We have an exciting presentation today. You can read it, I'm not going to read it for you. Dr. Abdelghany has been doing network simulation for as long as I have known you. We were actually in the same cohort at the University of Texas at Austin. He still talks to me, which is impressive, right? And that would put us back to 96 or something like that? 97, somewhere around that when we first met. And I have been very impressed with Dr. Abdelghany ever since. He's network simulation, plus many other things. Also, after you graduated, you went to work for the airlines for United for 3, 4, 5 years?
Yeah.
I didn't make you write anything, so now I got to see what do I actually remember. And then went to SMU, and he has been at SMU since 2004. Actually served as the chair for the past 5 years, which shows not always the best judgment, right? He took that particular position. But he does some fantastic work. We're actually currently working on an RVE project together. We're doing some energy emissions, and Dr. Abdelghany has actually modeled the entire Atlanta metro area in a DTA model. So if you really want to see how some dynamic traffic assignment works and work with the city of Atlanta, we now have the guy, right? So I'm really looking forward to this. I'm going to let you take off.
Thank you, Dr. Hunter. Thank you for the introduction. Just a great honor to be with you here today. And again, my presentation is divided into 2 pieces. The first part is a brief part. I'm going to give you an overview of some of the research activities that we are doing in our research lab at SMU. And then we'll dig deep in one of the newest problems that we are working on, which is in the area of real-time traffic management. Right, so we are trying to come up with a decision support system for robust traffic management. This is kind of the idea. This group is the first group that we are presenting work to. This is just hot from the lab to you here. So this is we have not presented yet outside. So this is kind of like an outline of my presentation here. So this is our research lab. It's kind of like, as you expect, mainly computational lab. We're working a lot with graduate students, postdoctoral and undergraduate students. So our lab is open for everyone. We get students every now and then to check what we are doing. But as I'm writing here, like most of our work, focusing on analytical and computational work of how we can achieve better design, better planning, better operation management for our infrastructure in the context of smart and resilient cities. This is kind of like maybe small paragraph summarize what we are focusing on. And of course, feel free to stop me if you have any questions, anything is not clear, feel free to stop me and I'll be glad to answer. So in the last maybe 7 to 8 years, we have been focusing on these 4 problems that I'm putting here. The one that takes most of our time is more in the area of real-time traffic management. So we worked, I would say, like for the last 10 years, started from a big project with USDOT and the Dallas Area Rapid Transit for the integrated corridor management. So we have a test bed in Dallas, and we were supporting all the simulation work for this test bed. And then also we did a lot of work internationally. We have worked on a group of professors from here, United States, and also from consultants to work on with the Saudi government on building like some simulation model for crowd dynamics in Mecca. And also like based on my experiences with United Airlines and airline, I still have passion for this area, so I'm still every now and then, especially I have a twin brother, he's here in every level, so still collaborating a lot, and both of us are working at United Airlines at the same time, so we do a lot of work in the airlines. And just recently, we are doing some work with the vehicle-to-vehicle communication, we're exploring some of that. I have here like 2 short videos to give you a glance. I hope that you have access to that. Give me security alert here, but there is something saying security alert, but I cannot take it off on my screen. There is something called like information security, but like I cannot take it. I have access to it with my mouth.
Can you say yes?
Just say enter. So going back to the area of real-time traffic management, so the problem here, as you see, we are talking about like a demand, travel demand that increasing significantly in the last two, three decades, and in the same time we have not expanded the capacity of our infrastructure at the same rate. So we see this big gap between the increase in the travel demand and the rate by which we improving our infrastructure, increasing the physical capacity of infrastructure. So this, of course, results in severe congestion. And with the severe congestion, we see also like a lot of like travel delays building up on our highway system, and also we see a significant increase in the fuel consumption. So this is like an example of the adverse impact of the congestion that we are seeing. So our research is kind of like focusing on congestion reduction. This is kind of what we are focusing on, how we can focus on congestion reduction. So the topic that I'm presenting today is like we are trying to build a additional support system that can help operators sitting in a traffic management center to come up with a scheme, right, with efficient traffic management scheme. So if this recurrent or non-recurrent congestion is happening, how can you respond efficiently to this congestion? So this is kind of the idea. And we are adding here, this is like a continuation of the work that we did before. We are focusing more on how to come up with robust scheme. And I will explain what I mean by that. So the robust scheme is kind of like, instead of like, because the problem is when you are trying to come up with a scheme for the congestion, you try to be proactive, right? You have to try to look ahead, so you do some prediction for the future. If your prediction is not accurate, right? If prediction for some reason is not accurate, of course your traffic management scheme will not be accurate, right? Or the effectiveness of the traffic management scheme that you are generating is not accurate. So what we are trying to say here, like, so if this is like, I have a certain like operational scenario that I think this is what will happen in reality, right? So I'm trying to come up with an optimal scheme to manage this situation, and hopefully this optimal scheme will come with the optimal performance. This is kind of the idea, this is how we do it. Like say, for example, if one of us were interested in optimizing traffic lights for the timing plan for a certain area, we go get some traffic volumes, right, and say, okay, this is the average traffic volume that will be there, so this is our input. Let's feed it in one of these packages that do like optimization for the signal timing, and then, okay, we will be happy by the performance, right? This is kind of the general idea here. But in reality, the picture is not like this. Right? In reality, that you could find different operation scenarios could really exist in reality. You don't know which one of them will happen, right? So you could have operation scenario number 1, so this is your input number 1, or number 2, or number 3, number 4. So different operation scenarios could happen. Each one has its own probability. Right? So this is kind of the problem here that we are dealing with. And if you look at a problem like this, so how can we design our system? Should we design based on, take an average of all those? Sometimes we do that. We look at all these operation scenarios and get the average one, right? As if like I'm going like Monday, Tuesday, Wednesday, I'm getting the average of all days and say I'm designing my timing plan based on the average day. We can do that. Or we can pick the worst case scenario and say, let me design for the worst case. So we can do something like that. Or try to be smart a little bit and say, I want to get a solution that will be close to whatever scenario will materialize in the real world. My solution will be close. My solution is still close to optimality, right? So in this case, we're looking more of robust solution. In this case, we're looking more at a robust solution. So to understand more what we mean by robust solution here, so define J as the system performance. Define J as my system performance. So maybe like if I'm looking at a sub-network, this is the average travel time or the total travel time for all travelers in the network. This is my performance here. So this performance, you will see it if you have a certain scheme, if you are implementing a certain scheme, and you have a certain operation scenario that happen, right? So if you have a certain operation scenario, maybe this traffic volume is what we see right now, and they have a certain timing plan, this combination together will give you G. Everybody see understand what G now? So it's a combination. This is the performance of the system, performance of the network, when you have a certain design with a certain input data set, right? So Here I'm showing like I have two designs, A and B, scheme A and scheme B. If you compare these two schemes, so now I have a scheme A here, and then these operational scenarios will change. Could it be changing from time to time, right? So the operational scenario will change, the performance of the system will change. So you will get kind of like a distribution for the performance. Same thing, if you have another design B, another scheme that you are trying to come up with, the same situation will happen here. You have different operational scenarios, they come with different probabilities, so at the end you get a distribution for your performance, right, for the system performance. So if you compare solution A and B, which one you prefer? If you compare A and B, which design you prefer? A design like give you a performance distribution like this, or a design that give you a performance distribution like that? Which one you prefer as an operator of the system? And why? Anybody helps me here? Yes.
You could want B because it has a more sustained higher performance, whereas A has more of a peak performance.
So let's say here the G representing the travel time in the system, the total travel time in the system. Right? G representing the total travel time in the system. So if I'm reducing my total travel time in the system, it's good. Right? So which one is better here? What I'm showing in this figure here to make it easy, here I'm showing the expected value, right, of this distribution. So like I have a design, I change the operation scenario will change, so my performance will change, right? But this is going to be the expected value of the performance. And for design B, this will be the expected value of the performance. And these two distributions, each one has its own variance. So this is the variance of this distribution here, this value here, and this is the variance of this distribution here. So in this case, which one would you prefer to have?
I think that A has much less expected value, and even the variance is not varying too much along the line. But as you were saying in the previous slide, wouldn't we go with existing scenario and pick our solution rather than this scenario? But yeah, here I would be going with A due to the reason.
Yeah, so here, yes, it makes sense to go with solution A, right? Or with design A, because compared to B here, no, it has less expected value, and also the variation of the performance is more controlled, right? So this is why in this case here, we say that A is more robust compared to B, right? We say that the solution A or the design A is more robust compared to design B. And if you look now that, okay, so I might come with different designs that sacrifice the expected value with the variance, right? So I can mean here, maybe I get more expected value and less variance. So this ends up giving us a set of like what we call the non-dominated set or the Pareto optimal set. So I can consider those are kind of like the Pareto optimal set of robust solutions. And then here I'm showing one of them, right? So this is kind of like an overview of what we mean by robust optimization here in the context of traffic management. Has this kind of like concept applied somewhere else? Yes, like if you do literature review, like you see this concept of robust optimization is popular in many problem domains, from power expansion planning to telecommunication networks, to logistics, supply chain, to financial planning, manpower planning, even like we have seen a lot of work from our colleagues who are doing network design, right? Robust network design, so I've seen a lot of work in that area. So many problems here, I'm giving you some examples of the literature that covers this work. In terms of like the application of this kind of concept in real time or traffic management in general, this work, and this started maybe 2008 by our colleague in University of Florida. He looked at a single intersection, right? And here, with the performance here, like used Webster equation, right, for the delay, and to try to come up with a traffic timing, like a timing plan that's different traffic volumes still will be robust. And then we started seeing people start moving to more on a network, but just a very small network, 5 to 10 nodes, 5 to 10 intersections. So this is kind of where we are. Most of the applications are offline. So yeah, the examples that I mentioned, I have a study area. I try to come up with robust timing plan for different traffic volumes that will come. Let me try to solve a problem like this. Also, that, as I said, here's a very simple representation of the traffic dynamics. Like one example, you just like Webster equation for the delay equation, and this is my performance. Here, like in Porsche, for example, they use like a cell transmission model for a very small network. So this is what we use here. There was an issue, of course, with the scalability, like scalability of all these models. Just for the typo here, scalability of these models for large network. That these models were very complicated to be scaled for larger networks. So what we are doing? What we are doing here, this is kind of representing the overall framework of how we solving a problem. We adapt to what we call a rolling horizon approach. A rolling horizon approach, meaning that like we have I would say two simulators. One of them is synchronized with the real clock. So this one's run minute by minute, trying to estimate what's happening in reality, minute by minute. And the other one is like doing short-term predictions. So this is like look ahead, right? Hopefully when we do the short-term prediction, we activate the shared support system here, and shared support system will come and give me a plan so I can go deploy this plan in the real world, and also my estimator module can also capture what happened in the real world. So this is the overall structure of the system that we are doing here. So let's look at this scenario here, and this is like, we have a paper published exactly in that area here. We were doing something like that. We say, okay, I want to do prediction. So I do a prediction. But at that point, we didn't think about that this prediction has coming from a distribution. So we were assuming this is the perfect prediction. This is our best guess, right? And then we go deploy it in the real world. But it could be a case like this, right? The real world could have a different operation scenario, that they are different from each other. So you end up coming with a plan that doesn't really match the real world. But when we published this paper, we didn't have the idea of robust. We assumed that our prediction is perfect, and whatever is predicted here matches exactly the real world. So this is a paper is accepted for transportation research, part C, very soon to appear. So this is what we're showing here, is more like extension of that. So see, no, it's not like this. Now, when you come up with if you're trying to predict, could be multiple operation scenarios. Each one of them has its own probability, right? So we are trying to come up with a solution that fits all these operation plans as much as we can, right? Something to state that my optimality doesn't change as this changes, right? As the operation scenario changes. So if in the real world you get any scenario, right? You get any of those, right? Hopefully you still stay close to all. This is the idea. But we're still making one big assumption here, which is what? We're still making one big assumption here. That we have perfect information on what? The distribution, right? So we assume I have perfect information on the distribution and the distributions that I'm used to predict my scenarios, and this is the distribution of the real world, and I assume these two are matched. This is the assumption that we are making, and in our experiments we'll try to see what is the effect of these distributions are different. We did some experiments with that. But at this point here, let's make this assumption that we have a lot of historical data, and from this historical data we are able to build some good information about the distribution of the operation scenarios. So again, this is like to give you an idea about the rolling horizon approach. So at each point here, you define a horizon edge, right? And then you try and you define the road, and then you move ahead. And so we are solving the problem now from what I'm showing right now. So I'm showing it for one stage. I'm showing the problem how we solve it for one stage, but this is repeated for all stages. So if we think about a system like that here, so at each stage here, what is the demand that I have in the network? I have two types of vehicles here. Vehicles that are already in the network from previous stages, right? This is the vehicle that already in the network from here. I know their routes, right? Because I know which route they are taking. And I know that in this stage, I have a new demand to be loaded. Right? This is when, at any stage, I'm just trying to understand what demand I have. So we divide them into two pieces. And this follows the work of Mohammed Sani and Professor Peter, right? This is like when we start doing the rolling horizon approach, they define the demand that way. So I'm not doing something different here. The demand has two components. One of them is like the traveler that already loaded from previous stages, so I'm tracking that, and the traveler that will be loaded during this horizon. So this is the demand. So if I want to get the performance of the network during this horizon edge, I call it G. So G is the performance of the network for horizon edge, assuming that I have BI is the operation scheme, the traffic management scheme that I'm implementing, and also I have an operation scenario S. So for this combination here, what is the performance of the network? So this case is going to be like, I know the traffic volume, I know the travel time. So again, I know the traffic volume, I know the travel time. So my performance function here is the total travel time in the network for travelers that continuing their trips and for the new travelers that are loading. So this is my G here that I'm trying to optimize. So if I'm trying to go robust now, right? So I might go with something like that. Make this my objective function here. Which is what? So I'm getting, this is my, if I have a certain scheme here, and certain operation scenario S, so this is my performance here, but now I'm going to look at what is the probability that this operation scenario will happen, and I'm trying to get the expected value. So here I'm kind of getting the expected value for the performance function, right? Considering the variation in the operation scenarios. This solution here, we call it risk neutral, because I haven't looked at the variance component. Right? I just looked at the expected value. I was trying to minimize, if you remember the graph, the Pareto optimal set, I was trying to minimize